Something quite tedious about the harmonic series is if we want to calculate its partial sums, it gets a little tedious the more terms you add. It would be great if we just had some closed formula where we could plug in an n and we get an answer directly, and we almost have something like that. Remember the gamma function? Something that's interesting is if we take gamma of z plus 1, we can perform integration by parts to get here. And because of the bounds of integration, this term goes to 0. So then when we pull out this z term, we find that gamma of z plus 1 is just z times gamma of z. This of course makes sense because if we think of gamma as a factorial, then z times z minus 1 factorial of course is equal to z factorial. Now I want you to direct your attention to this function, which we call the Digamma function. We obtain the Digamma function by taking the derivative of the log of the gamma function, which ends up looking like gamma prime of z over gamma of z. So consider if we took the log of gamma of z plus 1. From our definition of gamma, we know that we can split gamma of z plus 1 to z times gamma of z, and by our log rules, we know that we can split the product into a sum of two logs. Now we're going to take the derivative of these quantities. This one, of course, is the definition of our helpful Digamma function, and the derivative of log z is still 1 over z. So we started with the derivative of the log of gamma of z plus 1, which is of course the Digamma function of z plus 1, and we showed that that's equal to Digamma of z plus 1 over z. But this is of course the form we were looking for if we wanted to find a partial sum of harmonic numbers. The next harmonic number can be given by the last harmonic number plus the reciprocal of the next one. Now when we actually graph Digamma of z plus 1, we find that at 0, it's equal to around negative 0.57721. But we'd want it to be 0, so of course we have to add this missing constant. And wouldn't you believe it, the missing constant that we need is Euler's constant. And once we add this special constant, we see that we get the harmonic numbers we desired. So, wouldn't you believe it, the harmonic numbers function that we wanted all along was just the derivative of the log of gamma of n plus 1 plus some special Euler constant. Thank you very much for watching.